Hello, everyone. Welcome to the third unit for Earth Science called Historic Geology. So in this unit, we are really going to be building off what you've learned so far. I like to think of this unit as how do we read the history of the Earth? How do we read the story? Um, so we kind of started with rocks and minerals and rocks. And in my analogy of reading a book, learning about the processes that create different types of rock that the characteristics of those rocks and inferring its geologic past is really kind of like just teaching you letters and small words. So in historic geology, we're going to take it a bit further and we're going to kind of put those words together and string it into a story. So historic geology, you're really going to delve into the history of the Earth, how we divide Earth's 4.6 billion year history up, primarily based on changes in Earth systems. We'll always come back to that. Um, how we know what we know. And so I'm going to teach you quite a lot of concepts that allow you to at least explain um, why things are like they are and how we know this. And then, of course, as we delve into Earth's past, 4.6 billion years is a long time. So how do we divide that up for humans to understand? Because humans are really good at organizing information. So how do we divide that up? What is the basis for those divisions? Um, so we're going to get started today with a very um, logical concept, something called relative age. And relative age is really not looking for a number. It's just looking at older, younger. Compares how old something is to something else, which is younger, which is older. I am older than you. You are younger than me. That's relative age. We're not looking for a number. When we talk about geologic history, what we're looking at is what happened first. Well, then what happened? And then what happened after that? The numbers come later. The numbers come as we talk about absolute age, and we'll delve into that as well. But for today, we're just going to be focusing on relative age. So we're going to start with an idea that was proposed by a guy named James Hutton, a theory called uniformitarianism. So James Hutton was kind of the father of modern geology. He's a native of Scotland, and the idea that he proposed is something called uniformitarianism. It's a big word, but it's really common sense in that he just looked around and he looked at his native Scotland. He looked at the rock formations that are exposed, the rolling hills, the terrain, the topography, the evidence of things that have been occurring for long periods of time. Because most people at the time thought that the Earth was static and unchanging, that it is the way it is and it's always been that way. But what James Hutton saw with rivers eroding rock and scrapes in rock that looked like they had come from um, some kind of huge event. He looked around and he said that the things that occurred now, today, had to have occurred in the past, over thousands of years, even over millions of years, that these processes caused the landscape to change into what it is today. And so this idea is kind of the basis of modern geology, that the processes that occur today are the same that occurred in the past. The present is the key to the future. So in the present, we may have a process like erosion, weathering, deposition of material, and we can see evidence of that in rocks. For example, in this quick little graphic, we have these wind-blown sand dunes, and then when we look at rock formations, we can see evidence of this as well. How the rock is laid down and sand deposits on the far side of the hill as the wind moves upwards. So we're going to start with some very basic, again, common sense ideas about sedimentary rock, because sedimentary rock is really the the way that we understand a lot of concepts in relative age. The reason is because of how sedimentary rock operates, how it forms. Uh, so the first one that I want to talk to you about is something called the the law of original horizontality. Um, It's really common sense because it basically just says that sedimentary rock lays down horizontally. It lays down flat, um, just like that. So in this quick little graphic, you can see different layers of rock here, and they're all laid down nice and flat, nice and horizontally. If there's any tilting or folding of the rock, it had to happen after that the rock was laid down horizontally due to some outside forces. So quick little animation on that. Quick. So these rock layers have been laid down nice and flat. The tilting and folding that happens after the rock was laid down originally horizontally. So if we see tilting and folding, it had to happen after. Next. Oh, by the way, you can see all these nice flat layers of rock here, all laid down nice and flat. The next principle goes into the timing of how sedimentary rock is laid down. So it's laid down horizontally, but we also have this principle called superposition, which basically states that the oldest are on the bottom and they get progressively younger as you move up. So in this graphic here, much older than up here. We're actually moving back in time as we go further down into the rock. Quick animation. These cliffs, you can see younger, older, superposition. The rock layers are laid down nice and flat, law of original horizontality, and then they get progressively younger as you move up. Always think of it like a peanut butter and jelly sandwich. You have the bread on the bottom, then you put on the peanut butter, then you put on the jelly, and then the last layer. Anything that happens after this, anything that you see like folding, tilting, erosion, things like that, has to happen after it's laid down nice and flat, oldest to youngest. So tilting and folding. What we mean by that is the rock layers are tilted up, folded, crinkled, however you want to think about it. But compression forces within the earth, uplifting events like magma chamber moving up, pushing the rock up, lots of these things can cause the rock to change after it's been laid down flat. These changes in shape and volume due to just stressful forces. So in each of these graphics, or each of these pictures, you can see the layers of sedimentary rock that were laid down, but now they've been deformed due to some kind of pressure or changes within the earth. You have to be careful when you do relative dating with anything that's folded, because if they're folded over and you took a sample, your relative age dating techniques may not be as effective because they've been pushed over. So you could get a misinterpretation of relative age. There is a region in Virginia that exhibits a lot of tilting and folding. Of course, that's Valley and Ridge. Here we have the Appalachian Plateau, nice flat, horizontal sedimentary rock layers, but in Valley and Ridge, these have been deformed and folded. When we talk about folding, there's a couple of words I want you to be familiar with, something called anticlines and synclines. They're just fancy words for talking about the folds themselves. So in an anticline, that's the top part as it's pushed together, anticline up top, syncline down at the bottom. And again, they're usually caused by some kind of compressional stress that's causing the rock to be pushed together. The next thing I want to talk to you about is something called cross-cutting relationships. Cross-cutting relationships, again, helps us determine relative age, oldest to youngest. So in the picture that you see in the background, this is actually from the Grand Canyon. We have these nice flat horizontal layers of sandstone, but we had this intrusion it was lava because it's cooled to basalt. But you can see how it cuts across all those different rock layers. So when we talk about relative dating and cross-cutting relationships, anything that cuts through layers of rock, these sedimentary rock, has to be younger than the rock themselves, such as this intrusion of basalt across these sedimentary rock layers, or this fault line across these rock layers. And you can actually see that they match up perfectly, but it's just that they've been shifted down. So this cross-cutting relationship, this shifting down, this crack, this fold had to happen after the rock was laid down. Let's take a quick look at an animation. So here we have, again, a nice intrusion of some kind of magma or lava that cuts across these rock layers. It had to happen after the rock layers were laid down. In this animation, you can see the fault line that cuts across the rock layers. The fault had to occur after the sedimentary rock was laid down. I call it the jelly donut theorem. You have to have the donut, and then you inject the jelly to the inside that cuts across all those layers, but you have to have the donut first. Last topic, I think the last topic that I want to talk to you about is something called an unconformity. Unconformities are evidence of erosional events. It's a gap in the sedimentary rock record. So oftentimes we have and we find that sedimentary rock, of course, builds up nice and flat, horizontal, oldest on the bottom, youngest on the top. Very often we find an unconformity, which is just a missing piece of information. Typically what will happen is that erosion will remove almost an entire layer or an entire layer, and then a new type of rock can be laid down on top. So that missing bit of information where we have that erosional event is called an unconformity. There are three different types, and you're going to get into those into the reading, disconformities, angular unconformities, and nonconformities. And they each have their own specific types of events that they evaluate, but overall an unconformity is just missing information due to erosion. So in these different pictures, you can see rock layers were laid down, an erosional event happened, and then new rock layers were laid on top. It's just a gap in the rock record caused by erosion. Here's a nice, easy one for you to see. You can see the nice sedimentary rock layers that were laid down flat, oldest on the bottom, youngest on the top. They were then uplifted. That's why they're tilted like this. They were eroded down, and then a new rock layer was laid on top. This point where it was eroded down is the unconformity. Again, there's a reading in your textbook in Schoology where I'd like for you to go through and look at those three different types of unconformities. And you can just put your information into your notes if you're doing it that way. So with all this information, what can we do with it? With law of horizontality, with superposition, with cross-cutting relationships and unconformities, what can we do with it? Well, we can put it all together and look at rock and look at a sequence of events and talk about what happened first, second, third, fourth, fifth, oldest to youngest. So in this first practice, we take a look at these rock layers. We have P, we have K, M, S, we have A, which is an erosional event, unconformity, B, J, F, and then this intrusion R. So using these four principles, we can put together the story of this area. So how did we get this information? Well, a lot of times we can get it because they're exposed in a cliff face, but oftentimes we can take core samples, and a core sample is just when we take a drill with a hollow drill bit, very long, drill down into the earth, take up the sample, pull it up, lay that material out, and then look at the sequence of events, oldest to youngest, just like reading a story. So in this first example, we have the oldest on the bottom is going to be P. Rock layer P was laid down, then rock layer K, then rock layer M, than rock layer S. Here is where we have two different ways that we can go, and we're not exactly sure based on this information. We have to go into absolute age dating to find out for sure. We do know that R, this intrusion of magma or lava or some kind of volcanic material, we know that it's going to be younger than P, K, M, and S because it cuts across all of those three, principle of cross-cutting relationships. We don't know if S was taller, and that's as far as the intrusion went, but after all of this was laid down, some erosional event happened, an unconformity, which caused this here, A. Then after A, of course, B, J, F. So when we look at sequence of events for this rock record, we have P, K, M, S. R has to cut through all of those, then A, B, J, F. It's just putting it all together to tell the story. There are three other problems that I would like for you to look at. Number two, we have some folding and an erosional event. Number three, we also have a cross-cutting relationship, some erosion and some folding. And then number four, we also added in a nice fault line. What I'd like for you to do is try to interpret these diagrams. Start with the oldest, go with the oldest first, go all the way to youngest and see what you think. Here in this slideshow, I do have answers, an answer key, but please try not to use that answer key until after you've tried them, and then go back and see if you can figure out why you made or why you missed what you missed, or and check me. Also check me, make sure that I'm correct. If you have questions on it, please let me know. But I do have the answer key there. I want to show you one thing. If you think you're an expert, and a lot of people love this, I love this stuff. It's like a puzzle. If you really feel comfortable, and this is not for a grade or anything like that, but I'd love to see what you think of this website. So this is the website that was on the answer key. It's an older website. It's not very intuitive, not very nice, but it's extremely powerful in that it's very complex. So you have to think about all the different things that happen to create this geologic block. So you really start delving into the history of this area, wherever it may be, or it's probably just made up. So you determine the relative sequence of events in the diagram. You enter the letter of the rock or geologic structure or event in the sequence. You have tilting, you have folding, and erosion that don't have letters, so you have to type the word tilting, folding, or erosion in the proper position. Event 1 is the oldest. Event 20 is the youngest or most recent. There are no blanks. And once the events you've entered it in, just hit grade sequence. It's kind of nice because you can just hit grade sequence and then go back and fix it, try it again, and it'll tell you which ones you got wrong. But it's really tough, and good luck if you try it. I highly suggest that you at least try it and see what you can do. There's another one as well, even trickier, because there's a lot of things going on here from cross-cutting relationships. We've got rock material that has slipped down that you'll have to correlate. Actually, three rock layers that have slipped down. So it's much tougher than the other one. But again, if you're into puzzles and trying to figure this stuff out, this is excellent. All right, that's all I've got. If you have any questions, as always, please let me know. In the next class, we're going to add numbers to our interpretation of geologic history. We're going to look at how we know actual numbers. If the Earth is 4.6 billion years, how do we know that? How do we know what the age of a rock layer is, the actual number? So we can put that information together to get a better picture of the story of geologic time. Again, if you have any questions, please let me know. I'm here for you guys. Thank you so much.